Students, I think, would benefit from choosing SWOCC because it gives them an opportunity to get involved at a more hands-on level earlier in their career. Students choosing to come to SWOCC benefit from having opportunities at the freshman and sophomore level to get involved in research that can carry them forward in their career while still maintaining the same academic rigor as they would experience at a four-year institution. The day in the classroom in physics and engineering starts out as sort of a conversational approach to the material that we're looking at, whether it be solving rocket science problems, whether it be designing bridges, whether it be designing electrical circuit systems. It's usually a conversational approach that leads to a lot of questions. I always tell students if they're doing science well, they'll always leave science class with more questions than they got answers to begin with. And that's to drive the intellectual curiosity of the students. And that's what I try to do, making things interactive as possible and letting them foster that curiosity and develop those critical thinking and teamwork skills that they need to succeed as they go forward. You're dealing with a class in physics that's typically between 10 and 20 students. That gives you plenty of time to interact, ask questions. You get more direct responses from the instructor. And SWOCC being a small enough school, there are instructors that you will see a number of times, so you get to develop sort of a rapport with your instructors and truly do become more like mentors than they do become teachers. The biggest thing it brings is a sense of opportunity. It gives us a chance to revisit how our curriculum works. It gives us a chance to incorporate new ideas, new equipment, and it also provides the students with ample opportunity for new projects and new developments in terms of research. The physics and engineering programs at Southwestern are a great way to begin your journey in a professional STEM career.
So welcome everyone to our most recent installment of our Physics and Astronomy lecture series here at Southwestern Oregon Community College. I am Dr. Aaron Coiner. I'm the professor of physics here at Southwestern and the faculty lead for our engineering program as well. Always happy to have you all tuned into the live stream to learn about things on the frontiers of space and on the frontiers of physics and engineering. Today, before we get into the talk, I do want to sort of promote an upcoming event for us as well. I know we've had a lot of these talks in the last month and a half, but we do have one more scheduled for this term. The last week of May, on May the 26th, which is 2 Thursdays from now, we will have a student symposium that's going to feature some of our student research groups and their presentations of their research findings thus far, working with Dr. Springer in our chemistry lab, or working with myself in our physics and space physics engineering and atmospheric research group known as our SPEAR group. We have a number of different projects that I won't spoil for you guys for a couple weeks from now, but the May 26th one will actually have an in-person component, so feel free to come to the college and we will host you in our new Umpqua Hall Science and Health building in Umpqua Hall 184, which is our large lecture room in there. We will have the students giving their presentations. For those of you that can't make it, we will attempt to do a live stream with that as well, so that you'll get to see what our students are actually doing, along with the type of lectures that we bring into this lecture series on a normal basis. And for that, I'm grateful to the collaboration with Oregon Space Grant, with Dr. Mike Springer in the chemistry department, my project collaborator Crystal Hopper, and my students and Dr. Springer's students that will all get their just due by name when we do the student symposium in a couple of weeks. So please feel free to come by and support the students on the 26th. Today, I'm very fortunate to have the chance to have an invited talk from a colleague of mine from my time at Rice University as a student. She's also a research astrophysicist at NASA Goddard Space Flight Center in Greenbelt, Maryland, and another place that I used to call home. She's made more of a stable home out of it than I was able to. But I'm very happy to have my friend and colleague, Dr. Tonya Venters, as I said, research astrophysicist from NASA Goddard by way of undergraduate at Rice and graduate school at University of Chicago, to talk to us about the frontiers of astroparticle astronomy and what we can learn, astronomically speaking, from messengers that are not necessarily photons. Because for the longest time we were limited to photons, and now we have different ways of detecting different particles, which can give us more information. But better to have the expert tell you about that than me. So without further ado, Dr. Tonya Venters.
All right, thank you, Professor Coignier, for that introduction. And
It froze up. Oh. Brief technical difficulties, but we will. Hopefully, we'll be back in just a second. There seems to be some brief technical difficulties going on. We've had some fun with technical difficulties at NASA Goddard for today, but hopefully Dr. Venters will be back briefly. I will say that as we get ready for the talk, for those of you that are watching the talk on the live stream, if you have questions that come up during the talk, please type them in the chat in the live stream. I will monitor that, and then when we get to the Q&A, we will be able to answer those questions as they come up. I will make sure that everybody gets their questions in. I always like when people have questions because that means I have to come up with fewer of them. So if you have questions that come up, please feel free to share. We do encourage interactivity. It's just easier to have them all at the end when we do these types of remote remote live streams. While we're and since Dr. Venters is back, we will turn things back over to you.
Okay, hopefully that doesn't happen again. Somebody knock on wood somewhere. Okay. Well, as I was saying, thank you for giving me the opportunity to spend some time with you and talk to you about an exciting new phase of astronomy that we're basically just starting out on. What we're starting to learn is that there are several ways of doing astronomy, as Professor Coignier mentioned. And to get the full picture of the universe and what goes on in it, we'll have to make use of all of them. What I'm hoping that everyone will take away from this presentation, in addition to hearing about some exciting new developments in astronomy, is that when you go out and look at the night sky, you'll have a deeper appreciation for the fact that there is much more going on out there than meets the eye. Okay, so without further ado, let's go to the next slide. Okay, so this is, I guess, going to be sort of your tour, or maybe even a whirlwind tour through multi-messenger astronomy. So to give you an idea of where we're going, I'm going to give you a preview of the journey. So to start off, we'll talk about why it is we want to use multiple messengers to learn about the universe and everything that goes on in it. And then I will explain to you that there are 4 messengers that we're currently using to study the universe, and how each has its own strengths and weaknesses, which we should keep in mind when we're trying to do observations. And then I'll go into how we go about detecting these different messengers and what kinds of techniques that we use to do that. And then I will go into what we hope to learn about the universe from these different messengers. And then I'll finish off by showing you at least a couple of examples of how everything all fits together. Next slide. Okay, so to start off, give you a view of basically how you probably are accustomed to doing astronomy, and how we've been doing it, well, ever since probably the dawn of human civilization, or even before that. Basically, going out and using light, essentially. Here I have a picture of the band of the Milky Way galaxy that is taken from the ground. And you can basically, well, if you're in a sufficiently dark location on the Earth, which unfortunately is getting to be harder and harder to find as time goes on, you will be able to see, maybe not in quite such exquisite detail, but you should be able to see something kind of like this if you're in a sufficiently dark sky. Next slide. But one of the things that as time went on and we started to get, we started to get better at astronomy and started to develop technology to actually make more precise measurements and observations in astronomy, and doing other branches of science as well. We discovered that light isn't just limited to what we can see with our eyes. Light actually exists on a very wide spectrum, and the part that we can see is, of course, only a very small portion of that spectrum. So here I have pictured all the different regimes of light and what we call them. So starting at the very, very long wavelength and very low frequency end on the left would be radio waves. And just to give you kind of a sense of like how long the wavelength is, they have right underneath the names comparisons of like the sizes of different objects so that you can get a sense of just how big these things are. So radio waves are a very, very long wavelength to the extent that the approximate scale is about the size of buildings, as you can see. And then you continue up through microwave and infrared, and as you can see, the wavelength gets smaller and smaller and smaller. And of course, the comparison with objects gets to be smaller and smaller and smaller until all the way at the right-hand end, we get to gamma rays, which are where the wavelength is so small that you're looking at something that's on the order of the size of an atomic nucleus. But one thing that we really learned in doing astronomy is that rather than just limiting ourselves to technology that's sensitive to visible light, we can also develop telescopes that are able to detect light in all of these different wavelengths. And so I can show you what the outcome of that is, and that's on the next slide. Okay, so here's an example of what happens when you actually use the different wavelengths of light to study an object. So here I have, again, the band of the Milky Way galaxy, except now I've turned it around such that the plane is, in the middle of this oval, and the center of the galaxy is in the center. It makes it easier to orient ourselves. And along the bottom, I have different wavelengths that we've used to view the galaxy with different kinds of telescopes. So going from radio, and I realized that I should have thrown in gamma ray. Oh well. But radio and infrared gamma rays and X-rays. And you can see that when you look at the galaxy in different wavelengths, you can make out that there are different features that you're picking up on in all of the different wave bands that you may not necessarily be able to see in other bands. Some of them you can, some of them you can't. So you can see, like in radio, you kind of have this sort of arc that seems to be going up that seems to kind of sort of match a sort of arc that's happening all the way on the right end in the gamma rays. It's really hard to see, but there's arc there also. I'm sorry, on the right it was X-rays. there might also be kind of an arc in gamma rays as well. So the radio is actually showing you emission from electrons that have been accelerated in our galaxy and are now kind of circling around magnetic fields, basically. So in the next one, which is infrared, what we're seeing is starlight that is hitting dust, and that dust is actually reprocessing that starlight. It's absorbing it and re-emitting it in the infrared. And so what you're seeing here is dust emission, so you get a good picture of what the dust looks like. In gamma rays, what you're seeing is the sea of energetic particles within our galaxy called cosmic rays. And we'll talk a little bit more about cosmic rays a little bit later. Yeah, our galaxy is awash in these energetic particles that we think are accelerated, at least these cosmic rays, we think are accelerated in supernova remnants possibly, and then they basically go out in the galaxy. And what is happening is these energetic particles are crashing into gas, and of course also the dust and whatever, well, no, not radiation, but mostly the interstellar medium. And when it does that, it's producing the gamma rays that we can see on this plot. It may be a little difficult to see, but there are also some point sources that point to things like pulsars. And then there's some sources off of the plane that are extragalactic sources like active galaxies. And then in X-rays, it's probably a combination of several things. So it could be, the that I mentioned earlier. That's some of that emission, but there's also some thermal emission as well. And what we have also just right above in the little plot is the newly announced image of the black hole that's at the center of our galaxy, which isn't really exactly making this point, but you know, I had to throw it in there because it's new and it's cool. So, of course, the backdrop is the optical emission of the galaxy, which is basically all about starlight. Okay, so next slide. All right. Next slide. Okay, awesome. All right, so having learned the lesson that even just looking at different wavelengths of light teaches us different things about what kinds of objects we're studying in astronomy, we're really taking that to heart and taking this a bit further and saying, okay, well, we don't have to limit ourselves just to light. There are other messengers out there that we can also use, and they can teach us different things. So the 4 different messengers we have, of course, is light. Of course, that's still a messenger. It's down there in the bottom right. But there are cosmic rays, which I already mentioned, but you'll see a little bit more about a little bit later. Neutrinos and gravitational waves. And each of these I'll say a little bit more about. Next slide. Okay, so I have to start off with light. I'm not going to say a lot about it because, it's the one that everybody should be the most familiar with. But I do have to say a few things about it, which are, I mentioned that I was going to say, tell you that each messenger has its own strengths and weaknesses. So we should go through, like, what are the strengths and weaknesses of light? Well, light is fairly easy to produce. You basically get it pretty much everywhere. And so you expect to see, I mean, you're going to get a large amount of light whenever you're doing observations, at least compared to what you're going to get with some of these other messengers, believe me. Another advantage is that the technology that we use for detecting light and making measurements with it is pretty much tried and true. Like the telescope is on the order of getting to be about 400 years old, I believe. I think it is. It's about 400 years old. Some telescopes that we use in wave bands other than visible light, other than optical, are obviously not that old, but the idea of the telescope is definitely that old. So tried and true technology. Basically, at this point, what we're doing is making the technology better, more sensitive, but still pretty much the same idea. Another advantage is that light points back to its sources. It doesn't get deterred by anything in its path. You might be wondering, why is that important? Well, there's one such messenger that does not actually behave that way, and you'll see that a little bit later. But there are some disadvantages to light. It's easily absorbed by matter and radiation, so while once it gets started on its path, it's not going to deviate from that path from the source to us. But what might happen to it is, on the way, it might get absorbed by matter that's in its way, basically, or it might encounter other light and end up either being absorbed, or it might end up, if it's very high energy enough, it can create other particles. So there's kind of a limit to, especially when you get to high energies like gamma rays and very high energy gamma rays, there's even a limit as to how far away that light can come from if you're getting it. Now, that's a disadvantage in principle, because that means that if you're looking at very high energy gamma rays, there's only so far out in the universe that you can see. There's only so far back in history that you can see as a result. But on the other hand, there are some potential advantages to that, which means that the source can only be so far away. And that might help you in terms of limiting how many sources you might have to check for various things. But another thing is about light is, well, because it's pretty easy to produce, it can often be difficult to tell how it was produced. There are all sorts of processes that produce light. And if you're just getting light, sometimes it can be difficult to distinguish one process from another. And it's can be really annoying when you're trying to figure out what physics is happening in the system. Okay, next slide. Okay, so for the next two messengers, to explain those, I do have to take you back into history a little bit, not a lot, so bear with me here. But for the next two messengers, our story begins with the person on the left, Henri Becquerel, who discovered radioactivity in 1896. And of course, follow-up studies by Marie and Pierre Curie, really helped us to understand a lot about radioactivity and radioactive elements. So I say that the story starts there because, well, all right, so he discovered radioactivity. And at this point in time in history, well, we knew that the atmosphere could be ionized, like there's an ionization level. There are ionization levels in the atmosphere. And at this point in time, after he discovered radioactivity, everybody was thinking that the atmosphere, our atmosphere, was being ionized by radioactive elements on the ground that were releasing and ionizing the atoms of the atmosphere. If this were true, you would expect that as you go higher up in the atmosphere, that maybe the ionization levels would increase, but as you go high enough, eventually the ionization should start to fall off. Well, the person on the right, Victor Hess, did an experiment in 1912, and actually it was a few experiments that he did over a few years, actually, where he decided to go up in a balloon, and he went up pretty high. He flew up to a height of about 35 kilometers, actually, very high, and he took with him electroscopes that would allow him to measure the ionization of the atmosphere as he was going up. And so you can see, like, right next to him is the plot measuring the ionization of the atmosphere and finding that the ionization actually kept going up as he went higher and higher up in the balloon. And so what they realized was there's no way that you could have radioactive elements on the ground be able to do this. So there must have been something coming from outside the Earth, outside of the atmosphere, that was causing this ionization. And that's what's called cosmic rays. Okay, next slide. Okay, so what are cosmic rays? Following Victor Hesse's experiments, there were a series of experiments that took place, in the 1920s and the 1940s, where they eventually realized, okay, they were trying to figure out what cosmic rays were. Some people actually thought that they were gamma rays. It turns out that that is not the case. One way that they showed that was you could study, for instance, the variation in the amount of cosmic rays that you receive at different points on the Earth. So, like, you could study the variation over the latitude. You could study the variation between the western part of the Earth and the eastern part. And you can find that the flux of cosmic rays actually does change depending on where you are. And it changes in such a way that it actually correlates with the Earth's magnetic field. And this is how they determine, okay, well, if they were gamma rays are a form of light, and light doesn't bend or respond to magnetic fields, basically, at least so far as we know. But charged particles, as a matter of fact, do. They get deflected by magnetic fields. And so thus we were able to conclude that cosmic rays are electrically charged particles. With a few more experiments, like, for instance, measuring the penetration depth of cosmic rays in different materials, we were also able to determine that cosmic rays consist mostly of atomic nuclei. So you have here on the right a picture, which bear with me a little bit, but it's just there to remind you that you have all of the matter that we're familiar with is composed of atoms, and the atoms can be subdivided into an atomic nucleus consisting of protons and neutrons. And on the outside, you have electrons orbiting around the atomic nucleus. The cosmic ray is the thing that I've circled there, the atomic nucleus in the middle. Mostly cosmic rays, I'd say about 90% of them are consists of the nucleus of hydrogen, which is a single solitary proton. But there are some in that 10%, you get some heavier elements as well. So helium being a big one, and then more elements even going all the way up to iron. Next slide. Okay, so the next messenger would be neutrinos. And I'll say that around the same time that people were doing the experiments to understand better the cosmic rays, they were also trying to understand, radioactivity. And there are several different forms of radioactivity, but one of the ones that is most common is known as beta decay. And basically what happens in beta decay is, they didn't know this at the time, but I'm going to cheat and explain. It's pictured there on the right. The form that they were mostly looking at was what we call beta minus decay, where it's beta minus because the particle that they could see that would be emitted is an electron, which is negatively charged. But essentially, beta decay is a neutron is slightly unstable. And I kind of think of it as the neutron would actually prefer to be a proton. And so the neutron basically ends up becoming a proton by emitting a negatively charged electron, and also a neutrino, as it turns out. But at the time, they didn't exactly know this. And actually, when they first started trying to figure this out, they didn't even know that that there was a neutron. But eventually, they figured that one out. But what they were having difficulty figuring out was, okay, so for the other types of radioactivity that they were looking at, so things like alpha emission and gamma ray emission, the particles that would come out would have a specific energy. So, like for instance, here, the electron should have the difference in energy between the the neutron and the proton. The neutron is slightly heavier than the proton, and which is why it decays to a proton. And so the difference in their masses is what would give the electron its energy. But when the scientists of the day were doing measurements of the energy of the electron, they found that it doesn't have that specific value. Instead, they were finding that you get a spectrum of values that could exist over a range. So there was this missing energy that they could not explain. And these two gentlemen pictured here, the one on the left is Wolfgang Pauli, and the one on the right is Enrico Fermi, suggested an explanation for this. And their explanation was there must be a missing particle. And the gentleman, Enrico Fermi, named this particle the neutrino. So that is pretty much the story of this one. So I can go to the next slide. Okay. All right. So now that we've talked about what cosmic rays are, we can go into what the strengths and the weaknesses of cosmic rays are. So let's start on a positive note and go over the advantages. So the advantages of cosmic rays is they're relatively easy to detect. In fact, we've been doing this for about 100 years, as you can see. What I have pictured in this puzzle piece here is a cosmic ray air shower, where a cosmic ray comes into the atmosphere and crashes into nucleus, an atomic nucleus in the atmosphere, and then that causes a shower of particles. So what we've been able to do in cosmic ray research is basically study these air showers in order to learn more about the primary particle, the cosmic ray that created them. They're relatively easy to detect. There are actually quite a lot of them. And in fact, depending on what energy you're looking at, if you're looking at very low energies, you even see cosmic rays that, are associated with the sun, called solar energetic particles, but those aren't the cosmic rays we're talking about. But yeah, so it can be quite a lot of them. As with light, the detection technology is pretty much tried and true. We've been doing it for about 100 years, and any way it works out, it's pretty much a very similar technology that we've been using for quite a long time. So we don't have to invent new ways of doing it, though sometimes the strategies might change, and you might see a little bit of that later. As it turns out, the highest energy cosmic rays actually are the highest energy particles detected. And so there are some very interesting consequences or very interesting things that you can learn about matter and energy, potentially using cosmic rays. And of course, there's also a big question as to, okay, well, if they come from somewhere in the cosmos, something had to give it that energy. What was it that gave it that energy, and how did it do that? So we're very interested in that. They're sensitive to magnetic fields, but this is something that you could say, depending on what your interest is, it can either be a blessing or a curse. One thing I'll say, I list it as an advantage because cosmic rays are the only messenger that are sensitive to magnetic fields. So they're basically the only messenger that you can use to really probe magnetic fields that are out there in the universe. But of course, I said it's a blessing and a curse. And the curse is, well, because of magnetic fields, and that's what's pictured here on the right, cosmic rays get deflected, just like the cosmic rays that came to the Earth, and that's how they figured out that they were charged particles. They get deflected by magnetic fields, and so their path from their source to us is not straight. And so they don't point back to their sources. So as you can see with the little cartoon down at the bottom right, the cosmic ray is coming from the upper left corner. But if you try to follow its path back, once it finally gets to the Earth, you think it's coming from the bottom left instead of the upper left. And that's because it's been deflected by magnetic fields, not pictured here, unfortunately, but magnetic fields that it has encountered along its journey between the source and the Earth. Another consequence of the fact that their cosmic rays are deflected by magnetic fields is that there's no timing information, or at least they don't arrive in time with respect to the other messengers. And of course, it's because if you're going to get deflected along your path, it's just going to take you a lot longer to finally get to your destination than if you had gone in a straight line. Okay, next slide. Okay, so now neutrinos, strengths and weaknesses of neutrinos. So a strength of neutrinos is that they are not easily absorbed. And so, I mean, so basically, when you have a neutrino coming from some kind of cosmic source, you can actually use a neutrino potentially to study the insides of that source that in a way that you could not do with, say, for instance, light, because any light that would come from deep within a source is probably going to get absorbed. Not a problem with neutrinos. And so there are some scenarios where you can imagine where you should be producing light and you should be producing neutrinos, but you just aren't going to get the light from that. So if you only limited your astronomy to only using light, you're out of luck seeing that source. But if you could see neutrinos, you'd be able to see it. They do point back to their sources. They are electrically neutral, so they don't respond to magnetic fields. If you can get a neutrino track like the one that's pictured here, it should point to where it came from. Now, another thing that's an advantage about neutrinos is that they're actually relatively limited number of ways to produce them. Unlike light, which has a lot of different ways to produce them, such that you can't actually tell, sometimes you can't actually tell what kind of process is making them. Neutrinos are pretty much, you know that they come from, protons or neutrons or atomic nuclei doing something out there that's causing some kind of transition and leading to the production of neutrinos. And, you know, in a way that's similar to the beta decay example that I showed you. But you know that if you have neutrinos, it's probably involving processes involving those kinds of particles. Not true for light. But the disadvantage of, and it's a very big disadvantage, is that they are very difficult to detect. So this is kind of one of those things that the fact that they're not easily absorbed is both a blessing and a curse. They're not easily absorbed because they interact extremely weakly, and so they just pass right through everything. In fact, as a matter of fact, I recently learned that we have about 10 million of them per second passing through us, and we have no idea, basically. Well, as a result of that, it also makes them very, very difficult to detect. And so very often, if you have a detector, if it's not set up properly, then the neutrino will just pass right through it and you won't be able to see it. Okay, so next slide. Okay, so our final messenger would be gravitational waves, and around the same time that all of these developments were happening with cosmic rays and neutrinos, or not exactly the same time, but very similar time scale. We have Albert Einstein here, pictured on the upper left, was developing his theories about, well, starting with special relativity, but going into general relativity. And what's really important here is general relativity, because it basically just changed how we understand gravity. General relativity describes gravity as simply the curvature of space-time. And so whenever you have a massive object, like for instance, this star pictured here, and this grid thing right here, whenever you have a very massive object, it's going to curve the space-time around it. And of course, people like to use analogies like fabric. So they'll have like nylon stretched in like a sewing ring, basically, and they'll put like a very heavy ball in it so you can see the indentation. I wouldn't think of space-time exactly as a fabric, but it does make for a helpful analogy. But the idea here is that whenever you have a very massive object like that and curving space-time around it, if there's light passing by it, that light will, if it's passing close enough by that object, that light will end up being deflected, not because that object is pulling it with gravity, so to speak, but basically because that light is now following the curvature of the space-time. It is following the shortest path that it can, but now that space-time is curved. And so it led to some very interesting predictions. So the left here is attempting to portray, for instance, one classical test of general relativity, which is where you had the sun, and you had a solar eclipse. Otherwise, you wouldn't be able to see this. And as the sun was passing by a star, the apparent position of the star on the sky changed as a result of the fact that the light that was passing the sun was being bent by the curvature of the space-time around the sun. So that was a test that basically showed that general relativity was valid. A prediction that came out of general relativity was gravitational waves. So you could have, if instead of having, for instance, one of these objects, if you had two of them orbiting around each other, and especially if the characteristics of that orbit change over time, basically the curvature of space-time is also changing. And those changes in the curvature of space-time around those objects will actually propagate outwards, propagating being a fancy word for just traveling outwards. And other objects around will be able to feel that. And that's a gravitational wave. It says, yes. And so this is basically, the picture on the right is basically an artist's conception trying to sort of put this picture or show how gravitational waves can be produced. Next slide. Okay, so strengths and weaknesses of gravitational. Some advantages. Well, not easily absorbed. Okay, so that's a good thing. They do point back to their sources, although it can be a little tricky, and you'll see that a little bit later. But they are sensitive to compact sources and large masses. Especially sensitive to compact sources and large masses. You might get other messengers from those sources, but it can be a little bit difficult to tell what those sources are without additional information. With gravitational waves, well, with the technology that we have and the theoretical understanding that we have, you can actually get pretty good information on how massive the sources are that are producing the gravitational wave, and different characteristics like whether they're spinning and how far apart they are and things like that. So it's a ton of information that you can get that you can't really necessarily imagine easily getting with the other messengers. And a huge benefit of gravitational waves is that these signals include distance information. So I mentioned the theoretical understanding. That's put in the form of templates, and you can actually use these templates to try to compare with the signals that you're receiving. And you can put simulate putting the sources at different distances, and that'll change the amplitude of the waves that you're getting. And that's how you can get the distance information from it. It's very unique from the other sources. The other sources, it's very difficult to get distance information from. And we have to use some pretty sophisticated tricks to get that. But disadvantages, they can be pretty difficult to triangulate the source location. You essentially need, if you have a gravitational wave detector, you need to put them at different locations on the Earth, and we're in the process of doing that, basically. But you have to put them in different locations on the Earth, and like in the way that you would use use a device to triangulate radar and try to figure out where the signal is coming from. You have to do the same thing with gravitational waves. In order to improve the accuracy of localization for a source, you have to have detectors that are placed pretty far apart. And right now, we're really limited to putting things on the Earth, although there are discussions about putting things in space. Here at NASA, for instance, there's a whole group of people talking about that. And there are also people talking about trying to put one on the moon so that you can get even more precise source location information. But that's basically how far you have to go in order to get in order to triangulate the source and pinpoint it to its point of origin on the sky. Next slide. Okay, so how do we listen to the universe's messengers? Now that I've told you this beautiful story about all four messengers, what do we use to detect them? Next slide. Okay, so detectors for light. Okay, well, we talked about this a little bit, but basically telescopes, and of course your eye. But anyway, yeah. So what we have done, and I kind of alluded to this earlier, but just to sort of remind you, because that was quite a while ago. So we have built telescopes to pretty much detect light pretty much across the electromagnetic spectrum, or the spectrum of light, I should say. So down at the bottom, I have several examples of telescopes. We have telescopes that act like radio antennae to detect radio emissions. We have telescopes that are sensitive to infrared light. And so, for instance, the one that we just launched, the James Webb Space Telescope. And the reason we had to launch it is because infrared light is absorbed in our atmosphere. So in order to see it, we have to launch something into space most of the time, although there is an airplane that can fly really high and actually detect infrared light as well. And of course, we have the telescopes probably you're most familiar with, which are optical telescopes, where you can just look into the eyepiece and just look at your object, basically. Although typically we use very sensitive cameras to do very precise research measurements. And then there are X-ray telescopes as well. So, like for instance, the Chandra X-ray observatory pictured here that will measure X-rays. Now, what you don't see pictured here are gamma rays. And I will get into that in a second. But the reason you don't see it here is because, well, okay. For most of the examples that I've shown here, you're still in the regime where light pretty much behaves like a wave. And you can pretty much think of it as light rays that come in and hit a dish or a mirror and can get focused back to a secondary, either a mirror or a camera, depending on how you designed your telescope. Up here, if you have a mirror here, then it comes back like with the James Webb telescope into the center, and there's the camera in there. You can pretty much do that up through X-rays. There are some pretty high energy X-ray regimes where that gets to be challenging. And so it gets to be really, really hard to focus light, and you need special materials that you put on your mirrors in order to try to focus them. And usually they have a really, 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 really long boom, as they call it. Basically a really long focal length, because it's just that hard to focus those hard X-rays. Gamma rays, forget it. You're not doing that at all. So next slide. Okay, so one thing I should say about gamma rays. Okay, so gamma rays, now you're in the regime where light stops behaving more like a wave and starts behaving like an individual particle. And one thing I should say about gamma rays, this is a bit in an odd place, but it helps for the next part. Gamma rays, well, I will say this, you have to, okay, so the gamma rays, when they come into the atmosphere, they're in the regime where, okay, when they come into the atmosphere, they're going to encounter atomic nuclei, they'll encounter maybe electrons and things in the atmosphere, and they will actually interact with those things and create a shower of particles, much like the cosmic rays that I mentioned doing this earlier, basically. So there are essentially two ways that you can detect gamma rays. You can either go to space with a gamma ray telescope, so to speak, or you can basically, okay, you can have a telescope that's on the ground, and what they do is they look at the shower of particles that the gamma rays produce when they enter the atmosphere. And so what you see down here is the little telescope there that's looking up at the shower of particles. What this telescope is actually sensitive to is it's actually sensitive to optical light. But not that any of these particles are going to be optical. None of it's like optical light per se, but what it's actually looking for is some of these particles, or a lot of them, are going to be electrons. And those electrons are moving faster than the speed of light in the atmosphere, not in vacuum, but in the atmosphere. And when you have a charged particle that moves faster than the speed of light in a medium, that particle will actually produce radiation, and that's called Cherenkov radiation. And so that's what they're looking for, is Cherenkov radiation from these particle showers that were started by a gamma ray that came into the atmosphere. Okay, so next slide. Okay, so there are two ways that, as I mentioned, there are two ways that you can detect gamma rays. There's the direct way, which is basically you go to space, and this is pretty good for relatively low energy gamma rays. But you basically have a telescope that goes to space, like for instance, the Fermi Gamma Ray Space Telescope, where the box at the top of it is actually lined with, well, it has trackers inside, and these trackers have layers of silicon and tungsten. The idea is that the gamma ray comes in, And it starts, well, not really a shower of particles, but it actually kind of does start a shower of particles, because when it encounters one of the nuclei of either the silicon or the tungsten that's inside, the tungsten foil that's inside, it will actually end up sort of, it's energetic enough to create an electron and the antimatter partner of the electron, a positron, basically a pair. And that pair will continue through the tracker and eventually get measured by the gamma ray telescope. And the idea is that through each of these layers, you can tell a particle had passed through, and it passed through at this location. And then you can basically reconstruct where the particles came from, so you can reconstruct where they were, where the electron and the positron were created, and then reconstruct based on the geometry what direction the gamma ray came from. Okay, so that's an example of a direct detection. And the indirect detection is, as I mentioned on the previous slide, where they're looking for the Cherenkov radiation from particles from very high energy gamma rays that entered the atmosphere and interacted with nuclei in the atmosphere. And there are two examples of this. Well, actually, I should be a little more careful. You can even measure the particles, collect the particles from the showers themselves as well. And that's another example of an indirect detection. So on the right, I have two examples. You have the first picture, which is actually the Hess telescope. It's an example of what they call an imaging atmospheric Cherenkov telescope, where it's looking for the Cherenkov light from the showers. But at the bottom right, I have a picture of the high altitude water Cherenkov experiment, which is doing the second kind of indirect detection technique, where they're actually collecting particles from the shower and to trying to reconstruct the shower and trying to figure out information about the primary gamma ray from the particles that it collects. Okay, next slide. Okay, so moving to the next messenger, cosmic rays. They do this, they shower in the atmosphere as well. And so this is kind of, you'll see a pretty similar theme, where you have, well, there are kind of a couple of ways that you can look for cosmic rays as well. You can either do direct by going up either on a balloon like Victor Hess did. Yes, we're still doing that, as a matter of fact. Or you could even go to space and directly collect the cosmic rays that are either entering the atmosphere or before the atmosphere. Alternatively, you can do things with the shower itself if you have a ground-based experiment. So the cosmic rays, they make showers of particles just like the gamma rays, except it's a little bit messier. So the gamma ray showers, pretty much all you're going to get are these E pluses, that means positron, and the E minuses are the electrons, and the gammas are gamma rays. That's pretty much all you're going to get. But when you have a proton is it is a particle that itself has particles inside of it, 3 quarks, two ups and a down. And when it ends up striking an atomic nucleus, those quarks get excited and will start to break apart. But when they start to break apart, they end up, they don't broken apart. They'd rather stay together. And it's one of these, one of the few forces, or the only force that I know of, where if you try to break it apart, it actually gets stronger. And eventually these things, when they break apart, it says, okay, well, fine. It's actually easier for me to make more quarks than it is for me to be separated from that quark over there. And so you end up getting all kinds of particles. So like these things that you're probably not familiar with, or which is okay, you shouldn't be necessarily. these things like pions. So like there's this pi 0 and this pi minus. And then you can end up getting these muons, which are basically just heavier versions of electrons. Okay, next slide. Okay, so as I mentioned, there are two ways that you can look at cosmic rays. You could either do direct by the balloon like Victor Hess, or you could go to space. And we have done this. We have two currently operating cosmic ray experiments on the International Space Station, where basically they are they're kind of similar to the Fermi Gamma Ray Space Telescope, where they have these trackers and they have like this material. But this time, the cosmic rays come in, and they can do measurements with the cosmic rays and measure them directly, basically, by just collecting the cosmic rays themselves. Interestingly enough, so these two satellites, Voyager 1 and Voyager 2, which well, I grew up seeing pictures from them because before even I was born, they went out to the outer solar system and were taking pictures of the planets in the outer solar system. Well, both of these satellites actually have left our solar system. And, you know, they're still actually sending data to us, but since they're out there, they can actually do some measurements for cosmic rays all the way outside of the solar system. And actually, they can even do measurements of cosmic rays that we cannot do within the solar system, because in the solar system, we are surrounded by the solar magnetic field. And so the cosmic rays that would be coming from outside the solar system really can't make it in. But now, since they're out, they can do those measurements. And so there's potential there. Next slide. Okay, and of course there's indirect detection, in which I mentioned, where you can actually take advantage of the air showers that cosmic rays produce when they enter the atmosphere. And you can, the two experiments I showed earlier that look for gamma rays can also do measurements with cosmic rays using the pretty much the same technique, either looking for Cherenkov radiation of particles created in the shower, or by collecting the particles in the shower themselves. But another thing that you can look for with cosmic rays is as they interact with the atomic nuclei in the atmosphere, they can excite them. And it's primarily nitrogen, but they can excite the nitrogen nucleus. And when the nitrogen nucleus finally relaxes, it's going to emit light itself, and that's going to be in the ultraviolet. And we call that fluorescence. And so there are some cosmic ray telescope observatories that look for fluorescence light from these air showers. On the right, I have pictured here two types of cosmic ray facilities. Well, of this type, they're both giant arrays. And the reason is they're looking for the highest energy cosmic rays, ultra high energy cosmic rays, which by the time you get to those energies, cosmic rays are so rare that if you had a detector that was only 1 kilometer in area, 1 kilometer squared in area, it would take you a whole century before you would finally be able to see one, basically. So what we've done is in order to be able to see more of them and do measurements with them, we have built these huge arrays of detectors. So Pierre Auger is about 3,000 kilometers squared. It's in Argentina. And then to the right is the telescope array, which is about 600 kilometers squared, but it's supposed to grow by a factor of 4, as I understand it. And that one's in Utah. Now, eventually, though, you could try to grow your array so you can get more and more and more ultra high energy cosmic rays. But eventually there's a limit to how far you can do this. You don't want to just grow indefinitely, because eventually you're going to encounter mountains, and the terrain won't be even and things like that. So what do you do if you want to get more of them? Well, there's one thing that you could do. You could actually go back to space, but instead of directly collecting the cosmic rays, because similarly, you can't build a big enough detector to actually collect them. Instead, what you can do is look down at the Earth and try to see the fluorescence light from these cosmic rays by looking down at the light. Now, of course, if you're going to do it this way, you can only observe at night, which is why you see the United States there in just these specks of light, because it's nighttime in the United States. So one such concept that I was working on and that followed this idea was the Poema probe class mission that, well, we're still trying to get some funding for. So, okay, next slide. Okay, so how do we detect neutrinos? Well, okay, yeah, this is a theme that you'll see a lot of. Again, we're looking for Cherenkov radiation. Okay, but this is slightly more tricky because, as I've told you, neutrinos they interact extremely weakly, and so it's very, very difficult to detect them. So here I have two different kinds of neutrino detectors. The one on the left is one that's basically I don't know if it's actually a ball shape, but I think of it as a big ball filled with water, and it's actually built inside of a mountain in Japan. And the idea is that a neutrino that has basically passed through most of the Earth and finally makes it into this detector will interact with the water and create a shower of particles inside of the water. And the particles are traveling faster than the speed of light in water, and so that produces Cherenkov radiation. The one on the right is Ice Cube. It's a similar idea, except now instead what they have here is they built like a big cube, like 1 kilometer square cube of detectors, where they've attached these optical sensors that you see here, these circles, to these cords, and they have drilled into the ice in Antarctica and put these lines of detectors there to be able to have these sensors in the ice that would measure the Cherenkov light from neutrinos that pass again all the way through the Earth and then finally make it into the detector and interact with the atomic nuclei in the ice and create a shower of particles that will make the Cherenkov radiation. Okay, so next slide. Okay, so there's also another technique that we can leverage with the cosmic ray detectors that I showed earlier. They can also look for neutrinos under certain special circumstances, but it's basically they can only see one type of neutrino pretty much, or, well, I guess they can kind of see the other ones, but they have to be extremely high energy. But the idea here is that you have a neutrino passing through the Earth, and then it interacts with the particle in the Earth, and that particle or interacts with an atomic nucleus in the Earth, and it creates like, for instance, if it's a tau neutrino, it creates a tau lepton, which is an even heavier version of the electron, and that tau lepton will escape from the Earth and then get into the atmosphere, and then since it's really heavy, it's going to decay and try to become like either a muon or an electron, something lighter. And when it does that, it starts a shower of particles as well. And so these detectors for cosmic rays can look for the air showers from those kinds of neutrinos as well. Next slide. All right, and now gravitational waves. Gravitational waves, of course, you got to do them completely differently. Again, we're looking for ripples in space-time, and what you're trying to do is actually feel the ripples of space-time. So what we have here is, what we do here is we have like an L-shape detector, where the idea is that there's a laser that's being produced, and there are mirrors on either arm of the L, and the mirrors reflect the laser, and it comes back, and when they come back to this center here, the beam splitter, they form an interference pattern because it's low energy light, so now it's behaving like a wave this time instead of the gamma rays, which do not. And the idea here is that when a gravitational wave passes through, you can see it at the top of this little picture on the left, what it does is it changes the length of the arms ever so slightly as it passes through, or it changes the relative length of the arms. And so this will change the interference pattern that you see with the detector. And so that's how you can tell that there's a gravitational wave passing through. On the right, I show two of the gravitational wave detectors in the United States. One of them is the one on the left is closer to where you guys are. It's in Washington State. And the one on the right is closer to where I grew up. It's in Louisiana, where I grew up. And of course, my colleagues here at NASA are working on a space-based concept called LISA, where they're going to have 3 detectors in space, basically trying to do this kind of measurement. Next slide. Okay. There's another technique for measuring gravitational waves, but I don't really talk about it much later, so we can skip this. Next slide. Okay, so what do these messengers teach us? All right, next slide. Okay, so I mentioned that cosmic rays include the highest energy particles ever detected. To give you a little perspective as to what that means, I have here on the right the Large Hadron Collider, which is the most powerful accelerator that we have built here on Earth. And basically, in terms of how high in energy, well, the highest energy cosmic ray ever detected was about 10 million times what we're capable of achieving with the most powerful accelerator on Earth. So of course, next slide. Oh, I forgot about this slide. Okay, to give you even more of a perspective, if I were to try to build an accelerator like the Large Hadron Collider to be able to reach the energy of the highest energy cosmic ray ever detected, my collider would basically have to be as big as the orbit of Mercury in order to reach those energies. So that gives you a rough idea of what I'm talking about. Next slide. Okay, so of course, as you can imagine, well, with the Large Hadron Collider, what we're doing and what experiments its predecessors have done is it's actually studying the building blocks of matter. So looking for fundamental particles that are smaller than even protons and neutrons inside of atoms, basically. And we have here the current state of our knowledge of ordinary matter, the matter that we interact with every day, is basically can be decomposed into 18 different particles, essentially. And of course, well, the part of the reason for continuing these experiments is we want to know things about these particles, like, are these the only ones? There's dark matter out there. Is it actually composed of particles? If we could just get to higher energies, could we possibly create dark matter in the lab, for instance, or see particles that might be the dark matter? So of course you can imagine, with the energies that cosmic rays have, there's huge potential to do this kind of physics. Next slide. Okay. But of course, you can imagine that, well, in addition to the potential for particle physics, being able to do particle physics, you can imagine also, okay, well, how did they get their energies in the first place? If it's so difficult for us to accelerate particles, how does nature do it? I wish I could tell you, but I can't. Because, well, one of the reasons being, well, we don't know where these particles come from. And, well, of course, we don't know where they come from because, well, they don't point back to their sources. But we can imagine what these accelerators must have, what kinds of characteristics they have to have. So that's on the next slide. Okay. There are some criteria for the candidates. For instance, we can borrow some ideas from our friend, the Large Hadron Collider, which basically works where the particles are accelerated as they pass through along this ring. They're accelerated by electric fields. And as they get to higher and higher energy, they become harder and harder to contain, and they're actually contained by magnetic fields because charged particles are curved or deflected by magnetic fields. But when they get to too high energy, they won't be able to be contained any longer. So you can kind of borrow this idea and say, okay, well, for my criteria for candidate sources of cosmic rays, I can imagine, okay, well, if I borrow this idea of having a particle go around a ring, I can say, okay, well, my accelerator better be big enough for my particle to be able to still be inside of it, because it still needs, in order to reach high energies, and it better have a strong enough magnetic field to actually contain it and keep it inside of that accelerator, for instance. So are there any sources that we think fit the bill? That's on the next slide. Yeah, there are a few. And as a matter of fact, there are actually several. So ideas, for instance, like merging neutron stars or even just rapidly spinning neutron stars could possibly do it. They have the right characteristics. Or the jets of supermassive black holes, or jets that are created from dying massive stars. These are also called gamma ray bursts. And even if you could have like a supermassive black hole pulling apart a star, there are ways to be able to accelerate cosmic rays there too. But each of us have their own issues, and so there isn't really a favorite. Let's just say that. So we're left with the question: do they accelerate? Now, are there ways that we can tell? Next slide. Possibly. And this is where we're kind of starting to leverage the real idea of multi-messenger, which is using multiple messengers to get information. So we can't use the cosmic rays to point back to the source, or if we get up to high enough energies, maybe we could start, but you need a lot of cosmic rays in order to do that. So one thing that you could do is, all of the sources that I showed you have a lot of matter in them and have a lot of radiation. And when you get to high enough energies for cosmic rays, they will start to interact with that radiation as well, creating gamma rays and neutrinos. And those do point back to their sources. So you could use gamma rays and neutrinos to possibly try to see if a source is accelerating cosmic rays. Now, neutrinos are hard to detect, So we haven't seen a whole lot of them. So that's why we haven't already done this. And well, we've seen lots of sources that emit gamma rays, but we can't tell if that's because they're accelerating cosmic rays or if they're doing something else. Well, they could be accelerating electrons, for instance, which are not the cosmic rays that we're looking for. Okay. I think I might actually be over time. Am I?
I think you're okay if you've got a couple more minutes, but we could, but
Okay.
if you want to, we can do a couple more minutes and then we can do Q&A real quick.
Okay. All right. So I'll take a couple more minutes then. So next slide. Okay. So how does it all fit together? Okay. Well, I'll show you a few examples, and I'm glad I have a couple of minutes because there are maybe 2 or 3 more examples. Okay. So next slide. Okay. So we have a few examples where we already have started to leverage this idea of using more than one messenger. But we're really latching onto the idea of basically having 2 messengers arrive from an event in time and using both messengers to get as much information as possible. So one example where we've done this is, for instance, so one of the sources that I showed you a second ago was a supermassive black hole that was very vigorously accreting matter, and that matter is threaded with, it's got plasma, and that plasma is threaded with magnetic fields. And those magnetic fields can end up getting organized into jets. So that's what we mean by jets. These jets are actually really good places to accelerate particles. They're relativistic, so they already basically have particles, the plasma particles, moving at very high speeds, as a matter of fact. But there are other ways that you could possibly accelerate particles inside of them. One thing that we didn't know until possibly this latest event is whether they accelerate cosmic rays or if it's just electrons that they do this with. Well, recently we had an event where one of these kinds of sources flared, so it emitted it was basically producing light, and then that light basically ramped up, and so you got much more light than you had before. And that particular source we have been able to see in gamma rays before, but now we had more gamma ray emission. But what was interesting was that IceCube detected a neutrino around the same time that the source was flaring in gamma rays as detected by Fermi. And so that was possibly an indication that this source, somewhere in this source, it was accelerating atomic nuclei, i.e. cosmic rays, and those cosmic rays must have crashed into, probably in this source, probably it was light that's either inside the jet itself or from other particles being accelerated, or light that comes in from other parts of the system that comes into the jet. And, that's how it was creating the neutrinos. So that's one example of a multi-messenger case. Next slide. Another example was a joint detection between not just gamma rays, but basically light across the electromagnetic spectrum and gravitational waves. Here you had 2 neutron stars that were orbiting each other and then ended up merging, finally crashed into each other and merged to create a heavier object. When it did that, it created a gamma ray burst that was detected by the Fermi Gamma Ray Space Telescope, but it also produced gravitational waves that were picked up by LIGO and Virgo. I should say Virgo is the gravitational wave detector that's in Europe. And when the gravitational wave was detected, and people realized that was coincident with the gamma ray detection, everybody from who was operating a telescope across the electromagnetic spectrum just jumped on it to go try to look at it, because I mean, it was exciting. And one of the things that people were expecting to see was this little pullout that I have here, where it's a sort of artist's conception of a kilonova, where the idea is that as the neutron stars got closer and closer together, they started to tear each other apart and basically flung material everywhere. And when it flung material everywhere, it started creating heavier elements, and those heavier elements emitted light in the infrared and in the optical. So that's what people were looking for, and they did in fact see that. And so now this has profound implications for how heavier elements are created in the universe. Okay, so that's next slide. Okay, so you might be saying, okay, well, you just showed us joint detections between gamma rays and neutrinos and gamma rays and gravitational waves. What about cosmic rays? Well, cosmic rays, in either scenario, people have suggested that, well, clearly with the supermassive black hole with the jet, the idea is that obviously it is accelerating cosmic rays. And if the cosmic rays made it out of there, then, or if any of them made it out of there, then yeah, they would have been produced and they're there, but they are being deflected by the magnetic field. So they're still making their way to us, even though long ago we saw the gamma rays and the neutrinos, but the cosmic rays are still out there. And that's it kind of gives you an interesting perspective, or I think it's an interesting perspective, because the cosmic rays that we see now are signifying events that happened in the past, a long time ago. I mean, they're all happening in the past, but the cosmic rays are even further in the past because they take longer to get here. But the thing is, the light in the neutrinos, if you had any associated with them, they're long since gone. And same thing for the gravitational waves. So whatever happened before, the only way that we can study them is through the cosmic rays. Okay, so that's pretty much it. You can move forward, and so it should come up with my conclusions, so to speak. Okay, so the way forward is basically a reflection of the journey. It's basically the universe speaks using multiple messengers. We should listen. There are 4 messengers, each with its own strengths and weaknesses. And but I changed the questions to now, well, here are some lessons learned. Some messengers arrive together, others don't, but they all tell a different story. Exploring new territory may require getting out of our comfort zone, but doing so leads to groundbreaking discoveries. Okay, and then that's the end. Next slide. So the next slide should have, yes. So stay tuned for news that's happening in the multi-messenger astrophysics. I hope to be back here, sometime soon to tell you more about the exciting things that we've discovered trying to basically doing multi-messenger astrophysics. So thank you all very much.
And thank you for that. Thank you for that, Tony. And I guarantee you, when things come up, just let me know, and we will make sure that you are on the list to come talk to us again. Because as more information comes in this field, it's always good to keep everybody up to date on what exactly is going on. We did have a couple of questions in the chat that I'll start with. I actually had one question from one of my students, CJ, that asked early in the talk, you had said something to the effect of, in certain cases, neutrons would almost prefer to be protons. And he was asking, what exactly did you mean by that in terms of, or if you could clarify that statement as to.
Oh, okay. So neutrons, okay. So if you have, okay, so there are a couple of cases. Neutrons are slightly heavier than protons. And I mean, probably you've learned in like all sorts of science classes, just about everything, especially in the particle world, they want to do they want to be in the state that's the lowest energy possible. So atoms don't like to be excited. If you excite an electron, it's going to soon light to go back to its ground state. Same thing with an atomic nucleus if you excite that. For a neutron, and it can only happen in certain circumstances, but for a neutron, for instance, if it's by itself, it can be in a lower energy state because a proton is slightly lighter than it is, and so it can actually, in principle, be a slightly in lower energy state. So it basically is unstable, and it will decay to become a proton, basically. There are other instances where this can happen, and these are other examples of, for instance, radioactive elements, for instance. But the interesting thing is, in some circumstances, you can even have it go to a certain extent the other way around as well. So like atomic nuclei like to have about the same number of protons and neutrons. And so if you have like an atomic nucleus that somehow has too many neutrons relative to protons, then those neutrons are basically going to decay and become protons, or at least some of them will. Because the preferred state is actually to have about the equal numbers of protons and neutrons. And so this is how you have, for instance, radioactive elements, or radioactive isotopes rather, because those isotopes are a little unstable because they have too many neutrons, for instance, in that scenario. You could, in principle, also have scenarios where you have too many protons, and a similar thing will happen where, okay, there are too many of us. Somebody needs to become a neutron, that sort of thing. Yeah, those are kind of the scenarios where you would expect a neutron to decay to a proton.
Okay. And I had another one of my students. Yeah, I think that does. I'll see if CJ adds anything. But I had another one of my students, Joshua Nawatni, that asks about. You were talking about detecting cosmic rays either directly or indirectly, and he was asking, does one particular type of detection yield better results, or are there particular preferences as to whether they're direct detections or indirect detections?
Okay. So I knew I was forgetting something. I didn't quite, I guess, explain this exactly well. So, or I mentioned it, but didn't quite remember to clearly explain it. So, one thing that I didn't show was that the cosmic rays have a spectrum, and that spectrum falls fairly rapidly with energy. And actually, the spectrum extends, I forget how many orders of magnitude in energy. It's a pretty large range of energies. But over those ranges of energies, the spectrum falls by something like 20 orders of magnitude. So that's like where you start at the lowest end. By the time you get to the highest end, you've gone down by like 10 to the 20, or I think it's even more than that, like 10 to the 26. That's basically just how rare the highest energy cosmic rays end up being. So your preference for direct versus indirect is going to be dictated by what energy range of cosmic rays you're trying to study. So if you're looking at the low energy range where you have a lot of them, so you don't have to build a big detector, you just build a normal size detector and put it up in space or on a balloon, basically, then you can basically just collect the cosmic rays that you see, and you know that you'll have enough of them to do accurate measurements. But you're going to the highest end, you can't build a direct detection experiment, because then your experiment would have to be really, really, really large, or else it would just never see anything. So instead, what you would do is leverage the indirect detection technique so that you could build, for instance, a large detector on the ground, like those giant arrays that I showed you. Or you could, instead of doing it that way, you could do the other technique that I was describing, which is you could have a space detector that looks down, and it's actually looking at a very large volume of atmosphere. And that's a way of getting either a large array with a large area or a large volume of atmosphere. That's kind of a way of trying to collect more cosmic rays, not actually directly collecting them, but being able to see more of them. I hope that answers the question.
I think it does. I'm checking one more time to see if we have any additional questions, but I do appreciate your time, Tony. And like I said, next time there is something that comes up in this field, I'll be more than happy to have you come back, and maybe one of these days when travel is slightly easier, we can have you come out here and give a talk in person.
Yeah.
But it was It was good to have you come educate us in terms of this field. I admit I'm an astronomer. I follow these things, but I picked up the things on gravitational waves because we had a talk earlier this year by Dr. Raymond Fry, who works at the University of Oregon in Eugene and was part of the LIGO team that made the first gravitational wave discovery at LIGO. So we'd seen that part, but trying to tie it back together to all the cosmic rays and the neutrinos and the other particles and the other messengers. It's good to see it kind of piecing together as a larger puzzle.
Yeah. Indeed.
And with every bit of astronomy, whether it's what I do with solar physics or what you do looking at particle astronomy and cosmic rays, there's always so many different observations that we need to make to get a clearer picture of what we're looking at, that it's good to finally have the technology to be able to do most of it.
Yeah. So I find it an exciting field, and it's an exciting time for us now that we're finally able to do this, basically. And of course, now we're trying to do it even better now. So it does have the promise of some pretty amazing discoveries down the line, or so we think. So.
All right. Well, with that, I will go ahead and wrap us up. Thank you guys for all attending, and thank you, Dr. Ventures, for talking to us today. I do want to take the chance to remind everybody we do have our last geology lecture of the year that comes up this Saturday. Our dear friend, Dr. Ron Metzger, the geology professor here at SWOCC, is giving what he's tentatively titling the last lecture ? Recounting his history of almost 4 decades in the geology classroom and the various geology developments that he's been a part of. And then, as I mentioned earlier in the intro phase, be sure to join us back here for May 26th for the SWOCC STEM Student Symposium, where our student researchers that have been hard at work on material science for solar cells, meteorite collections, asteroid detections, and various and sundry other experiments will be able to give you all a short update on where their progress has gone. And that will again be May 26th at 7 o'clock here on campus in Umpqua 184. And the geology lecture on Saturday will be here on campus at the Hale Center, which is our performing arts center, at 7 o'clock on Saturday. Again, thanks everyone for attending, and we look forward to seeing you next time.